Okay, now we're going to look at solving systems of linear inequalities in 2 dimensions. So you can see here I've got graph paper on my screen. If you're going to take notes, I strongly recommend that you also use graph paper and probably have a straight edge nearby so you can graph straight lines since we are dealing with linear inequalities. We will assume that you already know how to deal with a linear inequality in 2 dimensions, as this video focuses on systems of those. So let's start with the first example, and the instructions for one of these might be something like graph or graph the solution set. Okay? It could even be solve, could be find all solutions, lots of different ways to word the instructions for these problems. But as with any system, we're going to have more than one, in this case linear inequality in 2 dimensions. So let's say the first one is y is greater than 1/3 x minus 2. And then the next one is 2x plus y is less than -2. And to indicate that this is a system, we'll typically put a left brace surrounding both inequalities. So what does it mean to graph the solution set for a linear inequality? Well, it means find all ordered pairs that make both inequalities true. So we'll kind of see how that works out. We need to find all ordered pairs that make both inequalities true. And since there's an infinite number typically, the easiest way to represent all of them is with a graph. Okay? All right, so you may have remembered that each of these, if you were to graph the solution set for each of these, you would get a half plane, right? A shaded region on the plane that indicates all the ordered pairs that make the inequality true. So when you have a system, what you're looking for is the overlap of those two shaded regions. That's the big idea. So let's get started. Let's start with y is greater than 1/3 x minus 2. Let's set up a plane over here. We'll use to graph. Okay, and just to keep it simple, we'll assume every tick mark here is 1 unit. All right. Now, if I want to graph y is greater than 1/3 x minus 2, I know I have a y-intercept of -2 because it's in slope-intercept form, and my slope is 1/3. So I need to rise 1 and run 3 to get subsequent points on this graph. And I could go both directions to get sort of the blueprint for my boundary line. So let me graph the boundary line for y is greater than 1/3 x minus 2. Looks something like this. Okay, so that's the boundary line for y is greater than 1/3 x minus 2, except there's no equals in the inequality. So I need to go back now, and maybe I forgot, maybe I didn't, but at some point you need to make sure your boundary line is dashed if the inequality does not have an equals. So this means our boundary line is not actually part of our solution set. All right, so that's the boundary line, and since we're going to have more than one boundary line, I strongly encourage you, and I will continue to do it throughout this video, I strongly encourage you to label the boundary line equation for each boundary line. So notice I put an equals here because this is the boundary line, it's not the inequality. Now, the other thing I recommend that you do is you talk about, because this is an inequality, we have to shade one side of this line, and so for the system, we have to shade the overlap of those two regions. So we're not going to really shade anything until the end. So we might keep track of where to shade for each of these independently. And since this says y is greater than, we need to shade above this boundary line. So if we were just graphing the solution set for this first inequality, it'd be everything above this boundary line, right? But we're not. We need to figure out where that region overlaps with the half plane from our second inequality. So now we need the boundary line for 2x plus y is less than -2. Now that's in standard form, it's not in slope-intercept form. So I think the easiest way to graph that is to use an xy table and find the x-intercept and y-intercept. So we're going to plug in 0 for x and find y, and we're going to plug in 0 for y and solve for x. So if this were an equals and x were 0, then you would basically ignore this term and you could see that y equals -2. So if x is 0, y would be -2. And similarly, if we made y 0, this term we would ignore, and that would mean 2x equals negative 2. And write this down if you need to, and then we would divide both sides by 2 to see that x equals negative 1. So negative 1 is our x-intercept. So let's plot those 2 points. So negative 1, 0 is here, and 0, negative 2 happens to already be plotted. And I can see the slope of the line now. If I want to continue mimicking that, go up 2 and left 1, I can get numerous points on this line just to help me graph a straight line. Again, this is why I recommend maybe using a straight edge here. I've got the software here to kind of help me draw straight lines, which is nice. So this is my boundary line for the second inequality, except this guy here also doesn't have an equal, so I need to go back and dash this boundary line. If you're doing this on paper, you might want to have the forethought to draw it as a dashed line to begin with. It might be hard to go back and erase. Now I need to label this boundary line, which is the equation 2x plus y equals negative 2, and then I have to decide which side to shade on. And the easiest way to do that here is with a test point. So I'm going to use the origin for my test point. So if I plug in 0, 0, I get 2 times 0 plus 0, and I'm asking, is that less than negative 2? So in other words, the left side, if I simplify it, 0 plus 0 is 0, is 0 less than negative 2, and the answer is no. So that means I'm not going to shade, the 0, 0 side. So 0, 0 is right here, the origin's right here, so that means I don't want to shade that side of this boundary line, I would shade this side. Okay, so now, if we go back now and kind of look at this, remember we need to shade above the first boundary line, and we need to shade the non-0, 0 side of the second boundary line, and the solution set for this system is the overlap of those two regions, which happens to be this region right here. So let me clean this up now. So the final answer is just all of the ordered pairs inside this region, which is open. You can see it continues to the left and it continues up. Okay, so it's an open region that goes on forever, but and really you could call it a quarter plane, right? It's 1/4 of the plane now. It's been cut into 4 pieces, and this is 1/4 of it. So that's our solution set. And oftentimes what you'll do when you have two boundary lines like this is your shaded region has corners. So in this case, the corner is this point right here, and that's called a vertex. And in this case, we only have one corner or one vertex. So the vertex for this region is the ordered pair 0, negative 2. That's obvious from the graph. So oftentimes when you graph a system of linear inequalities, you will also be asked to state the vertices, the corners of your shaded region. Okay, so this one's pretty easy. You can just tell what it is. Now I'm going to do another example here where we're going to have more than 2 inequalities and we're going to have more than one vertex. Okay, so we're going to get to that. But so what we're saying here with this shaded region is if you pick any ordered pair, such as, let's see what this ordered pair is, negative 1, 2, 3, 4, 5, 6, 7, 8. So this is the ordered pair negative 8. 1, 2, 3, 4, 5, 6. If you look at that ordered pair, this ordered pair is a solution to both inequalities. In other words, this ordered pair makes both inequalities true. Okay, and you could pick any ordered pair in this region. Now, the boundary is a dashed line, so the vertex is actually not part of the solution set. So points on the lines are not going to make both inequalities true, but anything in the shaded region will. All right, now let's do another example. And for the next one, let's graph the solution set. And let's state furthermore, let's see, graph the solution set. And state the vertices. There's going to be more than one this time. Sometimes there's only one. So in this case, the first inequality is a simple one. It's y is less than or equal to 2. The next one is y is greater than or equal to 3x minus 9. And the last one is x plus y is greater than or equal to negative 1. And then to indicate a system, I'll put this left brace. Okay. Let's go ahead and set up our plane over here, because we know we're going to graph this in a plane. Alright. Now we need to graph all three of these. Luckily, all three of these have equals in the inequality. So that means all the boundary lines will be solid, not dashed. So let's start with y is less than or equal to 2. So here's, again, we'll assume that the grid marks are 1 unit on this plane. So here's 2. And so the boundary line is the horizontal line at y equals 2. So I'll label this as y equals 2. And because it's less than, that means I will shade below. Okay, so we'll keep track of that. So we've got every ordered pair below this line so far. We're going to keep restricting that as we add inequalities to our system. The next one, y is greater than or equal to 3x minus 9, means we have a y-intercept of negative 9. So 1, 2, 3, 4, 5, 6, 7, 8. Here's negative 9. There's our y-intercept. And we have a slope of 3, which is 3 over 1. So we're going to rise 3 and run 1 to get subsequent points on the graph. Okay, so our boundary line for that guy looks like that. And again, it's solid. They're all solid. Let's adjust that just a little bit. All right. So this is the equation y equals 3x minus 9. And because it's greater, we need to shade above this line. It's in slope-intercept form, so that makes it easy to tell which side to shade. We don't have to use a test point. You can if you want. So remember, we're below this line and we're above this line. So the overlapping region right now is everything down here in this fourth. So just kind of keeping track of where we are. But we need to restrict that even further with our third inequality. So our third inequality, it's in standard form, so we'll use intercepts. If you plug in 0 for x, we can see that y is negative 1. If we plug in 0 for y, we can see that x is negative 1. So let's plot those points. 0, negative 1 is here. Negative 1, 0 is there. And we can continue with that pattern to get more points on our boundary line. I'm just kind of tracking it here, hopefully. There we go. All right, so that's the boundary line for the third inequality, which says that x plus y equals negative 1. And we need to use a test point here. We'll use the origin 0, 0. We want to know is 0 plus 0 greater than or equal to negative 1? So in other words, is 0 greater than or equal to negative 1? The answer is yes. So for this guy, we need to shade the 0, 0 side. Okay? So that means for this guy, here's 0, 0, so we need to shade this side of that line. Okay? Now when we take into account all three shaded regions, below this guy, above this guy, and the 0, 0 side of this guy, the overlapping region is everything inside this triangle. So sometimes your solution set will look like a polygon, a closed polygon such as this. Okay, so let's clean this up now. So our solution set is this region here, every ordered pair in this region. Okay? And really, the boundaries of this region are included now because they're not dashed. And you can see that we have 3 vertices, 3 corners of this shaded region, 3 corners. So since we have 3, we might label them with letters. So it's typical to label them with capital letters, so maybe A, B, and C. Doesn't matter what order they're labeled in. So we need to figure out what ordered pairs those are. Now, if you use a straight edge and you're very careful about your graph, you might be able to tell exactly what some of these points are. For example, we can tell that the ordered pair at A, because both of these graphs cross at the ordered pair -3, 2, we can tell that that ordered pair is -3, 2. That's a vertex. So let's label these as our vertices. B is not quite as nice. It does not land on a lattice point here, so we're going to have to do some work to find B. But C is pretty good. It looks like, because this guy went up 3 and over 1, and this guy went down 1 and over 1, we know for sure that this ordered pair is 2, -3. So the vertex there is 2, -3. So the only one that we don't know for sure is B. And you could use some basic principles of slope to figure out exactly what this point is without really doing any algebra. But I'm not going to get into that because that's sort of not a standard approach and is not always the easiest to do. So how do we figure out vertex B? That's the question. So to figure out vertex B, we have to understand vertex B is where the y equals 3x minus 9 line intersects the y equals 2 line, right? That's where those two lines cross. That's why it's important to label the equations of your lines. That's one of the reasons. Okay? So what we have to do is figure out where these intersect. And so what we have is a system of equations. And the easiest way to solve this system of equations is to use substitution. For example, I know that y equals 2, so that means I can plug that y equals 2 value in for y over here. So I get 2 equals 3x minus 9, and now I can solve this for x. So I'll add the 9, and I can see that x equals 11 thirds, which is the same, by the way, as 3 and 2/3. And if you look at the x-coordinate of this, well, it's 3 and 2/3. That makes perfect sense. But we still need the y-coordinate for B. So to get the y-coordinate, just like when we solve systems of equations, now we're going to take the x value and we can plug it back into this equation or to this equation. Now, it doesn't matter which one you do, you're going to get the same answer. However, there's no need to plug it in here and solve for y because this equation does not depend on x. We can already tell that y equals 2 no matter what x is. So we know that x is 11 thirds and y is 2. So that, and you can see that, you can already tell that from the graph, right? Y is 2 here. So the B vertex is the ordered pair 11 thirds, comma 2. So now we have the shaded ordered pairs. We have the region that represents the solutions to these inequalities, and we know precisely where the vertices are. Now, just a minor detail, most textbooks, most math software, this is what your solution would look like. You'd have the lines on there, you'd have the shaded region, you might list the vertices even. But really, the rest of the lines, they're not actually part of your answer. So you might want to go back and erase those. Now that can be a pain, right? That can be a pain. But I want to point out that technically all that stuff that remains now are not part of your solution set. So only this triangle, and since the boundaries are solid, the boundaries are your solution set. And again, that means if you pick any ordered pair in here, such as the ordered pair 1, 1, and you plug it in to all three of these inequalities, it will make them true. Okay? So that's just a quick way. If you want, you could check to make sure that this region makes sense with all three inequalities. It can be extra work, but it's nice to know that you can check your answer in one way or another. So that is a quick explanation of solving systems of linear inequalities in 2 dimensions. I hope you found it useful, and good luck.